Okay. An important application of superposition is when you have a situation where we have two charges, one positive and one negative, but each having the same magnitude of charge. And that's a situation called an electric dipole. So an electric dipole consists of two charged particles same magnitude, opposite sign. So we have a positive and a negative. There's a negative charge, here's a positive charge, and I'm going to draw them lying on the x-axis. And if we call this positive Q, then this is going to be minus Q, okay? Why are dipoles important? They show up a lot in nature, okay? There are molecules that actually are natural dipoles, okay? So the hydrogen chloride, for example, the hydrogen side, I believe, is more positive, and the chloride side is more negative. I believe that's right. So it's a natural dipole. It has what we call a permanent dipole moment, which we'll talk about in a second. Water molecules are natural permanent dipoles. One side is more positive than the other. And so this is an important configuration to take a look at the pattern of electric field due to this dipole, because we're going to be coming back to it over and over again. It's going to have lots of applications when we're looking at how fields affect matter, bulk matter, okay? So what we're going to do, and for the rest of this class, and we might be able to start some other things at the end, we're going to just take a look at the pattern of electric field qualitatively, what it should look like at various locations around this dipole. And then we will work out more formally the mathematics to give us an actual expression for calculating the field of a dipole. So we'll look at a couple of different observation locations. Okay, so here's our origin. This is y and x, and I'm going to look at a location on the x-axis to the right of this positive charge, call that A. I'm going to look at location on the x-axis on the other side to the left of the negative charge, call it B. I'm going to look at a location along the y-axis above the dipole, call that C, and down here on the negative y-axis, call that D. Okay? So just qualitatively, let's apply superposition to each of these points and see if we can find the direction of the net electric field. So location A, I ignore the negative charge for right now and just think about the direction of the field due to the positive charge. That's going to be pointing what direction? Everybody? That way. Okay. So that is, I'll call that E sub plus to indicate that's the electric field due to the positive charge. Okay. What about the field due to the negative charge? That's going to be pointing the opposite direction. How do the magnitudes compare? Which vector is bigger, E plus or E minus? E plus because it's closer. The positive charge is closer. So the field due to the negative charge farther away is going to be smaller. So when I add those two together, my net electric field points what way? To the right. Okay. Let's look at the other side. Location B. We have two field contributions again. E plus is pointing okay, ignore the negative charge, and notice that it doesn't matter that the negative charge is sort of in the way here. We can just treat it like it isn't there and think about the field just due to this positive charge. The field just due to that positive charge points to, away from it to the left. The field due to the negative charge points to the right. Which is bigger? The negative charge makes the larger electric field now because it's closer. What's the direction of E net? To the negative, yeah. Notice that E net on this side is pointing in the same direction it is pointing on that side. So already we're seeing a difference from, say, a single point charge, right? If you had just a positive charge, then the field would be pointing away no matter what side you're on. But in the case of a dipole, we're getting a different result, okay? Let's look at the vertical axis here. Let's draw at this location E due to the positive. That's pointing kind of, yeah, up like that. E due to the negative, down and like that. What's the net electric field direction? To the left. How do these magnitudes compare? They're the same, right? And if I wasn't clear, I'm drawing the origin halfway between the two charges. So if we call the distance between the two charges S, then this distance is S over 2, and this distance is S over 2, okay? So we've got a symmetric situation, right? The two magnitudes are the same. Their y components, the y components of those two vectors, how do they compare? They're the same magnitude but opposite sign, right? The x components are the same, right? So when we add these two together, we're going to get a net electric field pointing kind of like that. Kind of interesting, right? We get an electric field that's not pointing toward either or away from either one of those charges due to this superposition of the two fields, okay? Let's do it again for location D. E positive is pointing down like that. E minus is pointing up like that. E net points, yep, to the left once again. Okay. So we get this pattern where it's pointing one direction along the, you can call it the parallel axis or the axis of the dipole, and in the opposite direction along what we'll call the perpendicular axis, the axis that's perpendicular to the line that goes through the dipole. And we can do this at other locations, and it becomes a little tedious to think about it ourselves, but we can do this with the help of the computer. And if I show this little demo program, so we have our two charges. The red one is the positive, the blue one's the negative. We go through the same steps. So this green arrow points from the center of the axis, the center of the origin, to observation location A, to start with. We draw the two electric field vectors, the reddish one due to the positive, the purplish one due to the negative. Again, we saw that the E positive here is bigger, so there's a net electric field. Okay, we can move up to a location here and do the same thing. Calculate the two electric fields. Note that different magnitudes and different directions slightly. And when you add those two vectors together, you get a field that kind of points up and to the right a little bit, but not quite directly away from that positive charge. Do the same thing down here, and just from the symmetry, it kind of looks the same, only point has a negative y component now. Same thing here. We get a vector that now is starting to curl around. It's almost pointing up and to the left. And directly on the axis, we again get this vector pointing to the left. And we see sort of the opposite situation on the other side as the electric field from the negative charge is larger. And then we're back to this final point B. So we get this sort of pattern of electric field that as we move in a circle around the two charges, it kind of curls around. It's pointing mostly away from the positive end, mostly towards the negative end, but kind of curls where it's pointing perpendicular to the axis on this perpendicular axis. So this is sort of the classic pattern or classic dipole pattern of electric field, and it's something that you'll be playing around with in lab. You'll actually be doing a computer program that is similar to this, but you want to keep this pattern of field in mind and understand how to actually get it qualitatively, be able to go through the steps that we just did here to figure out the field directions, and just even if you want to commit it to memory, it wouldn't be a bad thing. Memorizing this sort of curling pattern of electric field as it points away, curls around to point directly parallel to that axis, and then points towards the negative on the other side. Okay? Because this is a pattern of field we're going to see over and over and over again as we go through this course. Okay? Questions here? We have a couple minutes, so let's try a question or two just looking at this. Let's see, what do we got? What if we change it up a little bit? So now I'm going to orient my dipole a little bit differently, but I'm going to look at a location C, which is along this line that's perpendicular to the axis of the dipole. So what is the direction of the electric field due to that dipole at location C? Okay, most people said direction 8, which is correct, right? Because it's just a matter, you could either think about taking this picture and just rotating it until we got the same orientation, or you just go through the same steps again, right? The electric field from the positive points away from that positive charge. The electric field from the negative points towards that negative charge. And so you get an electric field, a net electric field that's perpendicular to that axis, pointing up and to the left, like that. Okay? Next time we will be more quantitative about dipoles.